gases. Okay, emission spectrum, emitting the light. Everything else is in the background is black, so that's kind of like the anti-bright. Okay, and then the absorption spectrum is just the opposite of that, where the bright lines were, they're black, and so everything else is showing like these are absorbed. These colors are absorbed by that gas, but these are, since they're not colored in, it's saying that it's not absorbed, so it has to have been emitted, right? So it's just the inverse of itself. So on those, do not worry about making your colors perfect, but you will have to do some sketching on that one. So this is why I said this is an activity, not lab. Okay, it will go into your lab notebook. Okay, so let's do quantum. Okay, quantum, and then you should be somewhat familiar with quantum as you read through pages 1 through 16 on the reading guide. Notice that the rest of the reading guide should be read and outlined. And I'm going to check it tomorrow because we have some downtime tomorrow to work on some stuff. So lab analysis due tomorrow, and reading. So a lot more reading this unit, sorry. Anyway, so Schrodinger, we finally get to talk more about Schrodinger and his quantum mechanical model. And so with this one, we need to begin to really investigate the electron and where it is. And so this is just some background information about why his model is so different than Bohr's. But we're treating the electron as more as a wave. And so when you're reading, you probably saw this wave function where this was like the orbital where the electron could move. And you could see that it was moving in a wave-like pattern. And that's what it's saying. It's saying the electron doesn't just move in a circle, it moves as a wave because it has wave-like properties. It also has particle-like properties. Yet again, the wave-particle duality comes into play. So Schrodinger focuses on the electron more as a wave, but we understand that it is still a particle. It could have mass if you wanted it. You could pick up an electron if you really want to destroy your life, that kind of thing. So that's just a bit of background. So he said that electrons exist in these clouds. So the probability distribution of the clouds are, I'll have a picture for you in just a second, are more sporadic. The electrons are randomly in these locations, but they still form a general cloud. So you have a high probability the electron exists in this cloud. That's about it. But we can go deeper. We can kind of start to narrow it down. We can say that it exists in the S-shaped cloud. It's placed in the P-shaped cloud in the X or the Y orientation, and we think it's about here. So we can go down a little bit more specific for the address of the electron. But these clouds we now call orbitals. They're 3D. They're around the nucleus, and as a whole, when you combine all the orbitals together, they look like a sphere. That's why we draw atoms as spheres. We know they're actually not spheres. We know they're just a bunch of clouds of places where electrons exist. But I'll show you in a minute a picture of all those clouds overlaying each other, and it looks like a sphere because they kind of just take up every bit of space around the nucleus. So 99%, we are still only 99% probable of finding an electron in that area. Sometimes there's a rogue electron that jumps out of a cloud, and we have to track it down. So the clouds, they look like this kind of in general. You can see that they have that circular shape still, but they're not. You're not going to say the electron's going to be definitely in this ring right here. That's why they have these electrons that are randomly out there. So it's the higher the density, the more likely you are to find electrons in that general location. And so this right here in blue is a little bit more specific in the lingo we have to talk about. So we have to talk about nuclear penetration, which is always fun. So we're talking about the closer you are to the nucleus, that means your electrons are possibly undergoing nuclear penetration, meaning that the nucleus is so close to you, it's got you on lockdown. That's pretty much what it is. The electrons and the s orbitals specifically are so close to the nucleus that they're ridiculous to try to remove. So they're generally located, or they're going to have a really high density closer to the nucleus and the s orbitals. And then having a stronger hold on the electrons is really important when we get to periodic trends. So just FYI, you guys are going to, for periodic trends, we know a lot about them. So as a review, you guys are actually going to be making 3D periodic table charts and talking about the trends. And so you guys have a day and a half in class to do that in partners, and you guys teach part of it. So I really like that part to hear from you guys on the periodic trends. Anyway, so you'll have to recognize these probability charts, graphs, and every time you see a hump, that means that there's a large density, higher increased density of electrons in that designation, in that designated area. Not always will they be labeled here. Like I've labeled this as 1s and 2s, what you're essentially recognizing is that you're going to have a high amount of electrons at one distance from the nucleus. And then a little bit later, you're going to have another increased amount of electrons at the next set distance away from the nucleus. And then this one's has an increased probability just because there's more atoms with 2s electrons than 1s. No, that's vice versa. I'll tell you why in a second. And then you could go again, and this could be 3s. So anyway, this is showing you that you have set energy levels, or set orbitals away from the nucleus. Yeah?
Is 2s so far away from 1s due to the energy jump? Like,
This distance here?
no, I mean like the peak of the...
No, it's not, and I can't remember why I drew the peak that way, because I drew that. And there was a reason I drew it that way, but I'll have to tell you that in a second. Because that was me drawing of the chart, so I'll get there in a second. Okay, so those are called radial probability versus distance. So the distance is going to be the x-axis. Okay, so he just improved Bohr's model because he said not only does this model that I have work for hydrogen, it works for everything else. But we're concerned more about the quantum numbers that are associated with this than this whole background information. And I talked about that yesterday, so we're going here. Quantum numbers. These are the ones that you guys read about. Some of you guys are like, n equals what? I don't understand. This has been defined 5 times. I don't understand what n is yet still. So the quantum numbers are essentially an address for the electrons. The address comes in 4 numbers, like our zip code comes in 5 numbers, or your street address, your street, and then your city and your zip code. So the most broad descriptor of your address is what? What part of your address is very broad?
The country.
Okay, the country. Go one in. Let's go zip code. Okay. The continent, the world, the solar system, universe we are in. Okay, yeah. We could totally do that, but no. Okay, so we're talking about like zip code as a general. We're generally in 28027 or 28025 or something like that. So the quantum number zip code is going to be the principal quantum number. It's like, what energy level are you in? I'm in energy level 1. I'm in energy level 2. It's just talking about where the electron is in general. And so it's called the principal quantum number. That's a word you're just going to have to remember. Principal quantum number. And then the n is equal to the energy level. And generally the n is the period number. But not all the time, especially whenever we're talking about like going to n-1 electron configurations. The second quantum number is the orbital number. The orbital number designates the shape of that orbital. And these are literally numbers. You know, you're going to have 1 through 6. You're going to have some other numbers, 0 through something on this one. I'll get to that in a second. But, you know, it's kind of narrowing it down. We were in energy level 2, and now we're in orbital S. We're in the S orbital. So it's kind of like your street, which street you're on, but we don't know which house you are yet, right? So the shapes are going to be, S has a spherical shape, P has a dumbbell shape, D has a double dumbbell shape, 2 laid on top of each other, and F has more of a flower appearance, and I think that's approximately a flower. There's a lot of lobes in that one, so I'll show you pictures of those because I can't draw those really well. So the shape is just telling you of every orbital possible in that one, which orbital shape are we talking about, S, P, D, or F. Then we get a little bit narrowed down. We're going to see which house we're at. So on that street, maybe we're still talking about the p orbitals. P orbitals come in 3 varieties. The ones that go up and down, side to side, and in the board, and out of the board. We talked about this, yes? Okay. Sorry, I just did this in honors, and I can't remember what I did yesterday. Okay, so you have y-axis, x-axis, and z-axis. So which sub-level of the orbital you're in, which orientation of the orbital you're in. Then the last and final one is which person in the house you're talking about, which electron you're talking about. The one spinning up and the one spinning down. It's similar. Okay, never mind. Thank you. Okay, so scratch this for a minute, this information. But we do need to know we have electrons spinning clockwise and counterclockwise. So this is like my basics part, but let's go a little deeper. Principal quantum number. These are going to come in varieties, equals 1 through infinity, whatever number of periods we have. And this is some stuff I already said, but this information here and here, I think it logically makes sense, but I'm going to explain it anyway. So as you get farther and farther, or as you increase in energy level, it means you're increasing in distance from the nucleus. Because n equals 1 is the inside, n equals 2 is the next one, n equals 3 is the next one. So as you increase in the energy level, you're increasing in distance from the nucleus, which also means you're increasing in size of the atom, which is like atomic radius. Yes, ma'am, Grace. Oh, I thought you had your hand up. Okay. Maybe you're just like this. Okay, so as you increase in the number, you're also increasing energy because I explained this in honors the other day and they were rolling. So if mom is the nucleus and you're the crazy teenage boy or girl, then when you're close to home, you're a bit more calm and stable. Yes, yes, ma'am. No, ma'am. You're right here next to mom. So as you go out away from home, out here at the next energy level, or maybe out with a friend, you get a little bit more crazy, a little bit more energetic. Got that sugar high going, got the caffeine high going. I don't know what else, but you're a little bit more crazy. So you got a little bit more energy. So as you get more farther away from mom, nucleus, you get a little bit more energy, a little bit more crazy, a little bit more spontaneous and risk taker. I don't know. So I was always a goody two shoes. So I don't know about you guys. But less tightly bound by the nucleus means they have more energy, and we know that because we can do the Rydberg equation to prove that too. And there's that lovely picture again that Grace was drawing. So as the n gets larger, the amount of energy that it contains is larger, but these differences are minimized. Yes, ma'am.
Does like that have to do anything with like shielding?
Yes. So we're gonna talk about that with the periodic table trends, but I'll go ahead and say that now. In this, I'm gonna kind of scroll back up. In this image here, the energy levels that are here and here are shielding, like a shield, the attraction of mom, the nucleus, to the electrons that are out here. So the electrons that are out here are way more reactive because there's that shield in between that's limiting the amount of traction, or the length of the leash of the attraction between the electron and the protons in the nucleus. And that's related back to our Q1, Q2 over distance. The force of attraction, as distance increases, the force of attraction decreases. So the electrons are more crazy, more energetic, more reactive, easier to take, easier to use in chemical reactions. So we're going to talk about that a lot, actually. All right, angular quantum number. That's the second number we talked about. This is, yes, ma'am. No. Those were what we saw in our lab. Don't worry about that. No. Okay, angular quantum number is represented as L. It represents the specific sublevel. We're talking about the specific sublevels are S, P, D, and F. Okay, those are talking about those specific shapes. Then we just went through those shapes. The value of L cannot be determined without knowing the value of N. So that's because you have to know how many possible numbers you have that are available to be L. I'll give you a second to kind of wait, because I want to show you this one with my hands. And this is all in your reading. I printed out another quantum thing for you. It's just you need to read this a couple times to kind of, the lingo, the verbiage is very specific. Okay. So the L number is related to the number of possible orbital shapes, or I'm sorry, orbital orientations you can take on. Okay. So that's going to be related to our next number that we get to in just a moment. So the value of L is going to be, if you are an S-shaped orbital, you have a sphere, right? So you have to know that S is equal to 0. So I always do a fist. I'm like, okay, S, the L number, the angular momentum quantum number for S shape is a 0. And so that looks like a sphere, right? So that's a 0. The L number for a P orbital is 1. So I always remember start at 0 and then go to 1. And that's a dumbbell. And then to go to, so this one's 0. This 1 right here is our P orbital. And then D orbital is a double dumbbell, 2. Yeah? Mm-hmm. Double dumbbell. Can't do that very well, but it's 2. Okay? So pretty much the rule is whatever your N number is, you minus 1 from that, and that's going to be your L number, the possibilities of L number. So we can keep going, but like the number 3 here would mean that we would have a F-shaped orbital that we're specifying. A 4 would mean we're having a G-shaped orbital, which that's a theoretical orbital shape. We've never actually seen that. So these are just trends that we can increasingly tack on to if we discover more about the atoms themselves. So start off with 0, 1, 2, 3, 4, blah, blah, blah. Okay. As you increase these, you're obviously increasing in energy because these, lowest energy levels are going to have a lot of S's. Higher energy levels like 2, 3, 4, and up are going to have P's available. Only when you get to energy level 3 do you have a D available. Is there such thing as 2D? No, because the first energy level that we are able to enter D block is the 4th energy level is actually 3D. So that's why 3D, third energy level, minus 1 means D is equal to 2. And the first energy level you ever see an F block is going to be the 4th energy level. So that's definitely directly related. So they named the sublevels. I think there was something else I was going to tell you here. No, there was nothing else I was going to tell you. Okay. And so this was I tried to go through and add some examples, but you guys can see this. I think I just talked about this though. The principal quantum number 3, so n equals 3, has available S, P, and D, which is 0 because it's S, 1, P, 2, double dumbbell, 2. So n equals 3 has available these 3 different possibilities of its shapes of orbitals. But if I was n equals 1, what's my only shape or orbital shape available to me? An S, right? So your L number can only be 0, a sphere. Okay. So, and here are your different shapes. These are the orbitals of P. D looks a little bit more funky. Double, 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 double donut. Okay? That's just what it is. And then F. Okay. And there's some more. Those are all F. But there's 7 of them, yeah? 7 of them?
Why are they donuts?
I don't know. That was Schrodinger. I almost got donuts, but she said she wanted cupcakes, and the donuts look so good. Okay, so anyway, when you do get a chance to overlay all these balloon-shaped orbitals, and you kind of come to one common picture with them all in it, you can see them all together, it does resemble a sphere. So that's why we always represent atoms as spherical, even though they're actually not. Possibly not. Who knows? Okay, so ML number. ML is going to refer to the L number, which refer to the N number. Okay, so this is talking about the orientation, specific spatial orientation that the orbital we were just talking about, how it lays in the axes available to it. So the ML number is going to be dependent upon the L number, which is dependent on the N number. Okay, so if you have an L number of 0, what shape are you? What type orbital? You're the S shape. You're the S orbital. That's a sphere. How many different orientations do you know for a sphere? 1. So you get 1 ML number. You get 1 ML number, and that's a 1. Okay, let's do another one. If you have an L number of 1, which orbital are you? The orbital shape. You're the P orbital. How many different orientations does a P orbital have? 3, X, Y, and Z. Yeah? So you have 3 orientations. So you get 3 ML numbers. ML can be plus or minus L. From negative L to plus L. L is 1, so it's from negative 1 to 1, which includes 0, plus 1. So if you tell me the ML of negative 1, I'm going to assume that's the x-axis. If you tell me ML of 0, I'm assuming that's the y-axis. And if you tell me an ML of plus 1, then I'm assuming the z-axis. So these correlate with the number of orientations that orbital can take on, which is just the number of orbitals you draw in the orbital diagram. So in the orbital diagram, you would draw 1 orbital for S, 3 orbitals for P, 5 orbitals for D, and how many for F? 1, 2, 3, 4, 5, 6, 7. 7 orbitals for F. So the numbers of orbitals you would have drawn are these numbers here. They are directly related. So there should be 3 for the p orbitals. So next one you would do is, well, let's do ml. If our L number is equal to 2, we're talking about d orbitals. And d orbitals have 5 orientations, or there's 5 flavors of them, right? So we need to then say, all right, ml can be what, or what? Thank you. Does that make sense? It goes from the negative L version to the positive L version of it. And these would all be, I can't tell you the axes because they take on like x, y, and then y, z, and then z, y, and then y squared, z squared. They take on different things. All right, so the reason that we talk about these different sublevel, or these different orbitals of the sublevel D, is because these orbitals are all degenerate. I don't know why, but degenerate sounds like I'm just bashing these orbitals and sound awful, but the word degenerate in chemistry means the same energy. So all the P's that we would have labeled Px, Py, and Pc, they're all of the same energy. And that's why we it's so important to represent Hund's rule appropriately, because we have to, it's like equal access, equal opportunity. You have to put those electrons in each of those orbitals of equal energy before you go back and refill. So the word degenerate just means has the same energy. Oh, it's right here. Has the same energy. Okay. One more quantum number, and then let's go. Yeah, the last quantum number is real easy. It's talking about the spin of the electron, and that's plus or minus 1/2. So this is the last quantum number, and so we always refer to the plus 1/2 as the clockwise spin of the electron, and the counterclockwise as negative 1/2. So it's called the S or the ms number because it's just referring to the spin of the electron, so S means spin. That's the 4th quantum number. Okay, so then this is our complete address. This is like which person you're talking about in that house, on that street, at that zip code. Okay, and so we've heard Pauli exclusion principle or Pauli exclusion law before, but the reason it's called exclusion is because if something is exclusive, it's special, like exclusive offer at Kohl's today, just for you. So the exclusive part of it means that this set of 4 quantum numbers is exclusive to one single electron. So as you go forward, you just need to know that the theory of the quantum numbers is to supposedly allow us to identify one electron in any given scenario. Because if we can find the energy level, the type of orbital, the orientation of that orbital, and then say, oh, I'm talking about the spin that's going, the plus spin or the negative spin, then theoretically we can say we're talking about this specific electron. So it's like the address of the electron, which really is. And the Pauli exclusion principle is going to say that no 2 electrons can have exactly the same set of 4 quantum numbers. They can have the first 3 the same. They could be in the same energy level, in the same, p orbital, in the same or y-axis, something like that. They can be in the same x-axis, but they're going to be 2 different spins. So they can't have exactly the same. They can have the same 3 quantum numbers, but not the same exact set of quantum numbers. The 4th one's going to be different. So let's do some problems. Ready, Freddy's? No, not yet. Okay. The problems, I don't think did I print these for you? I don't think so. I don't believe I did.
Numbers.
I printed all the problems. How did you write this?
That was tea from yesterday
Oh,
when it exploded.
All right, I will come back here.
Yeah, you're good.
All right, so I'm going to ignore this for a second. Just talk about degenerate. Okay, so of these 2 quantum numbers here, how many electrons can be described by this? So how many electrons are in the 5th energy level? What does L1 mean?
P orbital.
P orbitals, okay. In a P-shaped orbital. So when you say P-shaped orbital, you're talking about the P sublevel or subshell. They have different words for this. So how many electrons are in the P sublevel of the fifth energy level? 6. P orbital can be that one, oops, or that one. How many electrons go into each orbital? 2 each, right? So 6 electrons. It doesn't even matter that I'm talking about like the fifth energy level. We're just saying of a specific energy level of those P, of that P sublevel, how many electrons can fit in there? 6 total, just like on the periodic table in P block, there's 6 electrons over. Yeah? Okay. If I had gone further and said how many electrons can be described by N equals 5, L equals 1, and ML is equal to 0, what have I just done? What have I just specified? The orientation of these. So I was just saying, oh, just P in general. We got this one, and this one. Now I'm talking about specifically in this orbital, this shape, this orientated one. I think that's the word. How many electrons are in there?
2.
Just 2. So if I go further, I'm specifying, okay, now I'm only talking about 2 electrons. But then if I go one more and I go, oh, okay, I want the S number to be plus 1/2. 1/2. I'm not sure what I just did with it. Plus 1/2. Then how many electrons am I talking about? 1. Because I have the 4 quantum numbers, which is exclusive to 1 electron. Okay. So if I just said how many electrons are in just N equals 5, no specifications what past that. A bunch, right? You can count them up on your periodic table, or I have this written down for you. I don't know where I put it. Rules governing. Haha. Okay, there we go. I was like, I know I have this. Write these 2 things down. Energy level, the quick way to do it is number of orbitals, number of electrons per energy level is 2n squared. So because of the ability to have 2 electrons per orbital, and then energy level you have, I don't know how that works out the 2, but it works out every time. But if you just want the number of orbitals per energy level, you just do n squared. So this is going to be number of orbitals, and then this is, if this is per orbital, take it for granted it's n squared. For every orbital, you're allowed 2 electrons per orbital, and that's where that 2 in the front comes from. So these are really good cheats. So n equals 5, theoretically, how many electrons are in there? Oh, and that energy level, sorry, I said energy level, thinking orbitals, 50. 25 squared is 25. No, 5 squared is not 25. 5 squared is
25.
I mean, squared. I was thinking 5 to the 5th. 5 squared is 25 times 2 is 50. Oh, Lord. Okay, go back and do one more problem with me. No, that's not what I wanted. Yeah, this one. Okay, what are the possible sets of quantum numbers for the 3rd electron? So we're talking about a specific electron. That means about 4 quantum numbers in the 4p orbital. So N has to be, or P has to be, L has to be remember the L numbers start off at 0, right? So this is 0, this is sphere, this is 0. So to be P, it would be 1, right? The ML number why? So the 3rd electron in the 4p orbital. So you means you got your 4p p orbital, the 3rd electron. Let's go with 1, only because I'm going to stick with what I said earlier. If this is 4px and this is 4py, this is 4pz, this goes from -1 to 0 to +1. Now we can't assume that all the time, but we're going to stick with our kind of general rule that we set for ourselves. So this would be also 1, and then the 3rd electron could, you don't know if the spin is positive or negative, so you would just put plus or minus 1/2. So there's 2 sets of quantum numbers, 411 positive 1/2 or 411 negative 1/2, because you don't know if this spin is up or down, because we always give that as a designation of up, 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 and then down, 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 but you don't really know. I don't really know either. Okay, so quantum numbers are not terrible. you gotta go back and just think about L and ML a lot. Okay? So you guys can look at the rest of your stuff, do your analysis, do your reading. Those questions that we're not able to do last night though, you want to do. And I'll give you guys a little bit of time in class tomorrow. So my game plan for tomorrow, I had to change a little bit, is I'm checking your outline, reviewing homework. You guys are doing an atomic structure, the atomic structure, electron configurations, and more worksheet. That's in your packet, just to get some more in-house practice with me. And then you guys are working on your periodic trends project I was telling you about a little bit earlier. So about half the classes work with me on stuff we've been doing, and the other half the classes start the project with a group. And I'll tell you about that one tomorrow. Okay? So you guys have a little bit more if you want to practice anything.
No, you're being called by Kara.
Oh, I'm sorry, Jared. Good S3. Yeah. I'm gonna get in trouble. I forgot to send you. Kara.